In this video, we're going to be talking about sampling variability and sampling distributions, specifically sampling distributions of a sample proportion. Sampling distribution of p hat. So we're going to use p for the population parameter and p hat for the sample proportion. Now, a sampling distribution is the distribution that would be formed by considering the value of a sample statistic for every possible different sample of a given size from a population. In this case, we're going to be using p hat as our sample statistic, which is the number of successes in the sample divided by the size of the sample. So looking at an example, let's suppose that we have the population of 6 students: Alice, Ben, Charles, Denise, Edward, and Frank. So we're going to keep the population small so we can find all of the possible samples of a given size. So we're interested in the population, or the proportion of the population of females, and this is called the parameter of interest. So what is the proportion of females in our population? So how many females are there out of the total population? And here we have there's 2 out of 6, which reduces to 1/3. So we're going to select samples of 2 from this population. So we want to know how many different samples are possible. So how would we calculate that? We could write out all of the samples, or we could find combinations of a population of 6 taken 2 at a time, which gives us a population of 15. So we're going to find the 15 different samples that are possible and find the sample proportion of the number of females in each sample. So we have Alice and Ben, which is 1 out of 2, or 1/2. Alice and Charles, which is 1 out of 2, which is 1/2. Alice and Denise is 2 out of 2, which is a population proportion of 1, or a sample proportion of 1 rather. Alice and Edward, which is a 1 out of 2, or a 1/2. Alice and Frank, which is a 1/2. And then we do the same thing for Ben, with each that he has not been with yet. And then Charles, with those that he has not been with yet. Denise, and then Edward. So here is our different samples and the sample proportions for each of those. So we want to find the mean and the standard deviation of these sample proportions. Doing so gives us a sample of p hat of 1/3 and a standard deviation of p hat of 0.29814. How does the mean of the sampling distribution compare to the population parameter, p? It's the same, right? So that brings us to our rule 1 in our general properties for sampling distributions of p hat. So we're saying the mean of p hat equals p. And our second rule is that the standard deviation of p hat can be calculated by taking the square root of p times 1 minus p, all divided by n. Now, note that in the previous student example, the standard deviation formula was not correct because the sample size was more than 10% of the population. Now, rule 2 is exact if the population is infinite, and it's only approximately correct if the population is finite and no more than 10% of the population is included in the sample. Let's move on to a different example. So the development of viral hepatitis after a blood transfusion can cause serious complications for a patient. So the article "Lack of Awareness Results in Poor Autologous Blood Transfusions" reported that hepatitis occurs in 7% of patients who receive blood transfusions during heart surgery. So we will simulate sampling from a population of blood recipients. So we're going to generate 500 samples of each of the following sample sizes: n equals 10, 25, 50, and 100. And we're going to compute the proportion of people who contract hepatitis for each sample. Now, the following histograms display the distributions of the sample proportions for the 500 samples of each sample size. Are these histograms centered around the true proportion, p equals 0.07? What happens to the shape of these histograms as the sample size increases? And that's going to bring us to our third rule. When n is large and p is not too near 0 or 1, the sampling distribution of p hat is approximately normal. Notice that as our sample size increases, our histograms look more and more normally approximated. Now, the farther the value of p is from 0.5, the larger n must be for the sampling distribution of p hat to be approximately normal. So we have a conservative rule of thumb here. If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then a normal distribution provides a reasonable approximation to the sample distribution of p hat. Let's go back to our blood transfusions. So we're going to let p equal the proportion of patients who contract hepatitis after blood transfusion. And we're going to let p equal 0.07. Now suppose that a new blood screening procedure is believed to reduce the incident rate of hepatitis. Blood screened using this procedure is given to about 200 blood recipients, and only 6 of the 200 patients contract hepatitis. So does this result indicate that the true proportion of patients who contract hepatitis when the new screening is used is less than 7%? To answer this question, we must consider the sampling distribution of p hat. So our p hat is 6 out of 200, which is 0.03. So now we need to ask ourselves, is the sampling distribution approximately normal? So we're going to take our n times p. So that's going to give us a value of 14, which is larger than 10. And we're going to take our n times 1 minus p, which is going to give us 186, which is also larger than 10. Now, because both of those values are greater than or equal to 10, yes, we can use a normal approximation. So we want to know, what is the mean and standard deviation of the sampling distribution? So the mean of our p hat equals 0.07. And the standard deviation of our p hat is going to be 0.018. So does this result indicate that the true proportion of patients who contract hepatitis with the new screening is used is less than 7%? So we're going to assume that the screening procedure is not effective and that p equals 0.07. So we want to find the probability that p hat is less than 0.03. So we're going to standardize our value, and that's going to give us a z-value of negative 2.22. And we can calculate that using our calculator, or can look it up in our table and get a z-score of 0.0132. So here we're saying that we have a 1.32 chance. Now, this small probability tells us that it is unlikely that a sample proportion of 0.03 or smaller would be observed if the screening procedure was ineffective. So this new screening procedure appears to yield a smaller incident rate for hepatitis.